Okay, so my research interested in also particle oscillation, hydrodynamic simulation, and code development. So if you're interested in some code development or hydrodynamic simulation, please feel free to contact me. And yeah, let's begin my talk. So cosmic ray is ubiquitous in our universe. And we know their presence by measuring the emission from them, such as the radio emission from radio galaxy jet or radio emission from the radio rally. Or these cosmic ray particles directly encounter the Earth's atmosphere atom, then they break to the lower energy particle or to generate radiation. We call this air shower. So by measuring air shower, we know their energy and their species. So we can generate the spectrum of this cosmic ray, something like this. And the energy flux of cosmic ray is something like this. And the energy is extended to the 10 to the 21 electron volts. It is very high energy. And especially cosmic ray, which has an energy above the 10 to the 80 electron volts, we called ultra high energy. It is literally ultra high energy cosmic rays. And these particles are first observed in New Mexico in 1962, and these particles are continuously observed. So there are two observatories of ultra cosmic rays, which is TA, telescope array, located in the Utah State. They observe northern hemisphere. And one is the OJ Observatory, located in the Argentina, and they observe the southern hemisphere. And interesting part is the origin of ultra cosmic rays is still debated. And here is another interesting part here. The observational data has discrepancies between these two observatories. The first discrepancy is found in the energy spectrum. As you can see here, about the 3 times 10 to the 90 electron volts below, they had a great argument in the cosmic ray flux. But all of that energy range, they has discrepancy there. And also in that range, they had that discrepancy in mass composition. So according to all the observatories data, high energy flux is lower than TA data, and the mass composition is higher than the TA data. And this is well known in this field, but interesting thing is that there's no model or theory for explain this discrepancy. And I mentioned that the cosmic ray, ultra energy cosmic ray origin is still debated, but there is a first candidate. This diagram called Killas diagram, and sometimes we call the confinement condition, because this diagram shows the maximum energy of particle which some system can confine. And this relation came from very simple assumption that the gyro radius of the cosmic ray is greater than system size, then cosmic rays are easily escape from the system. So if the gyro radius is equal to the system size, then we can get energy, and that is the maximum energy that system can confine. And here, the radio galaxy jet can confine 10 to the 20 electron volts proton. So we thought about that. This radio galaxy jet is one of the most promising candidate for generating ultra and cosmic rays. But note that it is related to just confinement, not related to the acceleration or generation of this particle. So in this diagram shows the radio galaxy jet can confine this energetic particle, but not means that this can generate this particle. So we have to study the particle oscillation phenomena in the red galaxy jet. So the aim of this study is how can red galaxy jet can generate the ultra cosmic rays, and can they explain the discrepancy between the observational data? So we perform the relativistic hydrodynamic simulation here. This cartoon shows the initial condition of this study. It is 3D simulation, and this is one of the animation of slice view density profile. So we perform the relativistic hydrodynamic simulation through our newly developed high order code. And the jet power is covered the observed jet power range. And you also adopt the background profile. It is well known as the beta profile or king profile. So we assume that this jet is advanced with the ICM cluster. And we directly put the particle and see the oscillation process. So here is the concept of this simulation. Here's the red galaxy, and inside the circle, this is the host galaxy. And inside the host galaxy, there are numerous supernova remnant shell is there, so they generate galactic cosmic rays. And these galactic cosmic rays can affect with the jet flow, and they can oscillate it. Actually, that is the re-oscillation. So the initial cosmic ray distribution is following the galactic cosmic ray distribution. And this is the animation of how we simulate this problem. So you can see the time evolution in the background. There's a jet flow, and this circle is the cosmic particles. And the color indicates the log scale energy. So ultra energy cosmic ray is above the 10 to the 80 electron volt. So the green to yellow color particle indicate the ultra energy cosmic rays. So you can easily find that the ultra energy cosmic rays are well generated through the oscillation in the jet flow. But how they can oscillate, that is the problem. So there are three oscillation mechanisms. First is the sharp oscillation. Here is the slice view of the spatial distribution of the sharp Mach number. And you can easily find that there's a numerous shocks are generated inside the jet induced flow because we using very high order relativistic hydrodynamic code. And shock is basically the compression flow. So particles are scattered around this shock, then they continuously gain energy. We call this a diffusive shock oscillation, and this process is sometimes called Fermi first order oscillation. And through this oscillation, particles are generate the energy spectra at a power level. And the slope of the power is depending on the compression ratio of the shock. And for instance, the strong shock, the strong non-relativistic shock, the energy spectrum is followed e to the -2. And there's a strong shear is generated. So here the purple is the jet flow, and the other side they generate so-called backflow. So the surface of the jet flow and backflow, there's a strong shears are generated. And similar to the shock oscillation, particles are scattered around the shear layer, then they effectively gain energy. And through this shear oscillation, particle also has a power law distribution. And it is also related to the scattering model, but generally through the shear oscillation, particles' energy spectrum is much harder than energy spectrum generated by the Sharp solution. And there's strong shear there, so Kelvin-Helmholtz instability generates strong turbulence along the jet spine. So here is the turbulence spatial distribution, and turbulence is basically the random motion. So particles are scattered around this turbulence region. Then sometimes they gain energy and sometimes they lose energy, but statistically they gain energy. So we called this process as a Fermi second order oscillation. And this Fermi second order oscillation is much slow process compared to the Fermi first order oscillation. So which process is most dominant process for generating ultra high energy cosmic rays? So the answer is here. This diagram is relative contribution of each oscillation process. So for instance, for the energy 10 to the 60 electron volt particle, they generally gain energy through the shock oscillation. So ultra high energy cosmic ray has energy above the 10 to the 80. So we can easily find that the ultra energy cosmic ray gain energy through the shear oscillation, especially shear generated at the jet and vectoral boundary. So this is one of our finding. And the next is let's talk about the energy spectra. So through the oscillation in the gas flow, they generate the double power law with exponential cutoff energy spectra. Equation is here. So you can see this double power law shape and the exponential cutoff here. So the first slope, which range is below the E break here, they have a very hard energy spectra. It is because of the shear oscillation. I mentioned before that through the shear oscillation, the energy spectra is generated very hard spectra. And here is most interesting part here. Where is the exponential cutoff in this model? And that is the interesting part. So exponential cutoff is generated as a function of the Lorentz factor of the jet. So for instance, if the jet is mildly relative stick speed, then exponential cutoff will appear not very high energy. But if the jet has a relative speed, then this exponential cutoff is generated very high energy. So this is comparison between our model and previously people in this field using the model. So previously, people just using the energy spectrum from the source as a simple power law with exponential cutoff, because they just assuming that there is some strong shocks are there, so they just using e to the minus 2 energy spectra, power law spectra. But we here suggest new model for the source energy spectra. So the question is that this model can help resolve the difference between the observation data. That is the question. So we use the CR-propa code and simulate the cosmic ray propagation simulation. And this propagation simulation includes photopion production and photodisintegration and electron pair production and redshift modules. So I briefly compared to the difference of the two models. So first panel shows the energy spectrum at source, and second panel shows the energy spectra that we observe. And solid line indicate the energy spectrum from relativistic jets, and dashed line indicate the energy spectra generated by the mildly relativistic jets. And color indicate the mass of the particles. So for instance, red line is proton, basically proton. And you can find that in high energy region, if there is relativistic jet, then more flux are generated, something like this. And another interesting part is that if there is relativistic jets, then lighter element is much more than the non-energy spectrum from milder relativistic jets. So this phenomena generates some kind of this trend, mass composition trend. So let me summarize this slide that if there is relativistic jet, then high energy part flux is more immense, and the mass composition will be lighter. And we track the distribution of the radio galaxies close to the Earth. And interesting part is that in northern hemisphere, there's a Virgo A, which has a relativistic speed. While in southern hemisphere, the dominant radio galaxies are Bonus A and Centaurus A, but they has not very high Lorentz spectre. So Centaurus A has a Lorentz spectre considered as 1.2 to 2. So we generate the energy spectrum from these radio galaxies, and the final result is something like this. So in left panel, it shows the energy spectrum, and actually that is a flux, and the mass composition of northern hemisphere through generate our model. And right panel shows the flux of southern hemisphere and the mass composition in southern hemisphere. So in northern hemisphere, I mentioned that there's a Virgo A which has a relativistic jet. So the flux is enhanced compared to the southern hemisphere. And the presence of the relativistic jet, the mass composition will be lighter than the southern hemisphere. So let me summarize my talk that ultra energy cosmic rays can generate through the jet acceleration from the relativistic jet, the jet from the radio galaxy, and relativistic jet generate higher flux of ultra-energy cosmic rays, and they and the lower mass composition. And in northern hemisphere, there's a relativistic jet which came from which emits from the Virgo A, so they can have a discrepancy between the observational data from the northern hemisphere and the southern hemisphere. Okay, that is all, and thank you for listening, my talk.
You're very interesting as well. Yeah, wonderful. So I just have a question regarding to your second bullet point. So I'm a little bit confused that for your relativistic jet, you have lower mass composition. So does that mass composition refers to electron positrons? And don't you expect that if you have more energetic, jets, there is a more possibility to create them? And I noticed that all the way from lower energy to higher energy, that was lower than the mild, relativistic one. Am I missing something, or is this really expected to be the case?
Actually, the particle is not came from the jet itself. So jets are considered to generate the electron positron, as you mentioned, but these particles came from the host galaxy, and jet just reaccelerated particle. So it is not related to the jet material itself. So
that jet component can also elevate, it can also create pairs, right?
Okay.
I mean, how do you know whether this comes from the ambient matter or from the jet? Doesn't mean that you have to have in general more relative, more pairs than the. Okay, maybe we can just say that.
Okay.
Yeah.
Okay. Thank you.
Okay, maybe you can shout very loudly.
The question is about three different physics to generate the cosmic or accelerator, the cosmic ray. The first the shock, the other is the shear, and we also have the turbulence acceleration. So may I ask what's the major physical parameter to determine the fraction of each component in the contribution to the cosmic ray?
So you mean that this part, I think.
Yes.
Right, yeah.
So what's the parameter or the physical parameter determine each part? Because you said no matter how fast the jet increase across the distance, it is still that the shear component will be the major one.
Yes.
So what's the underlying physics?
So the shear is generated at the jet and backflow boundary. So the strength of the shear is strongly depending on the Lorentz factor of the jet and the momentum of the jet also. So if the jet Lorentz factor is reduced, then shear is generated much weaker. So I didn't show the much diffusive the jet flow here, but if the shear is if the Lorentz factor is much lower, then shear ratio will be reduced, and they will generate more turbulence and shock. So then the contribution of shock will be increased. Is that your question? Okay.
I have a question. So in the beginning of your program, you showed a picture of a shower in the Earth's atmosphere. I was just wondering, that's not a real picture, is it?
Yes, that is not a real picture. It's just drawing some.
Drawing in an air shower.
Yes.
Over a picture, okay.
Yes.
Well, let me just say that this topic is something I've been, I don't work in this field, but I've been wondering about this for 50 years, and this seems like a really good explanation of where these cosmic rays actually come from. So I'm very pleased to learn this.
Oh, thank you so much.
All right, I think you still have some slots available, so if people want to sign up to meet with you, please feel free to continue the conversation there. Otherwise, let's thank our speaker again.
Thank you so much.
Probably this one will be enough. Yeah. And then you go to the file of the presentation.
So,
Okay,
next
lost it.
introduction. So, you might get this. So our next talk is going to be Mikhail.
If you don't mind, yeah.
Okay.
Okay.
How do you pronounce your last name?
Medvedev.
What is it? So,
Excellent.
I'm usually a faculty member at the University of Kansas and holds a 10% appointment at MIT. However, he's on sabbatical this year, visiting
Is it better?
Yep, try again.
From the last.
Oops, completely wrong. Okay, let's do it again. Yes.
I'd float.
Uh-huh.
Yeah.
Thank you. Sorry for this technical difficulties. I'm a theorist, so it's not a surprise that we have technical difficulties. That was a joke, actually. So what I'm going to talk about is the heliosphere, how we can model it, should we model it, and also other astrospheres and what can we learn and whether we can learn something from that. So this talk is not going to be just presentation of what we've done. We've done something, but of course there is a lot of things to do, and I want to encourage you, and actually this talk is kind of an advertisement and kind of push, if you want, on the community to actually pay more attention to this and to jump into this research, especially because we have everything at our disposal. So it's not something that needs to be developed from scratch. We have lots of things. So first of all, what do we see here? This is the heliosphere. Of course, you should recognize this, even though nobody really flew that far to see the heliosphere like that. What we see here is the sun. Oops. The sun is over here in the center. Then there is this little bubble, this cross section. Actually, not it's not a cross section. It is just line of sight integrated. I mean, integration along a certain direction. Then we have this termination shock, and we have a long helio tail going in the direction opposite the direction of motion of the solar system through the interstellar medium, local interstellar medium. The size of this graph is about 10,000 AU. What you see here in addition is not just the sun and the termination shock and the heliopause and the heliosheath, but also, first of all, those green ripples. The green ripples are actually color enhanced density fluctuations. So the color coding here is such that to enhance the density fluctuations, to emphasize the Kelvin-Helmholtz instability at the heliopause and the heliosheath. It is time dependent, and the time scale of changes here, typical time is like a year or 2 or 3, not long. So it's actually, if we want to make observations, you just need to do several observations year after year of the same point, and then you will see a signal, time-dependent signal, which you can take out and analyze, even if there is lots of foreground and background emission. Foreground from charge exchange from the inner heliosphere, background from the galaxy. In addition to that, what you see here is the bow shock. The bow shock is not really strong here. It's not in color enhanced specifically here, but it's there at Mach number of about 2. Some people say actually even less than that. And you have ripples here. What are those ripples? The ripples are actually sound waves. These are sound waves which are produced in the local interstellar medium because the solar wind velocity is dependent on time with 11-year long cycle. So that's what you see there. It's changing ramp pressure. Changing ramp pressure causes changes in the density propagates, density fluctuations propagate as sound waves. So there is lots of dynamics here, and we can recover all that. I'm not saying that we do pick up ions here and everything, all the physics relevant here. It's all done routinely nowadays. How one can observe? Well, you have already seen there the statement that solar wind charge exchange is a good thing to use. Why is it important? I'm going back to this slide, and I'm sorry I'm spending so much time on this single slide, but believe me, that's really important. We don't really know anything about the local interstellar medium around us. Generally, we know, but once we do those computer simulations, we have no idea what the boundary conditions are far away. We don't know whether it is turbulent medium or not. We don't know whether we have velocity shears or not. We don't know what kind of density fluctuations we have in the interstellar medium. We just assume it is static, the sun is moving through, and the density is constant. That's it. And we also know magnetic field is there, and assume the magnetic field is homogeneous as well. That's really simple assumption for assumptions in general. And any type of fluctuations should affect how this heliopause and the tail look like. Whether the tail is dispersed, whether it's bent, whether we have those fluctuations, Kelvin-Helmholtz fluctuations or not. Maybe magnetic field suppresses it in certain directions. All those things need to be answered. And we don't really have probes of that. We do have two probes that fly through, which are the Voyager 1 and Voyager 2, and New Horizons is heading there, but it takes a while. But recognize these are just lines of measurements. It's a single point of observation at a given time. You can't really construct much from that. Yes, one can do something with it. And of course, Voyager data is used to actually check that those simulations are correct, and some modifications are done to the inner boundary conditions at least to have that simulation match the Voyager observations. But in general, we have lots of unknowns here, and it's possible to observe. And the whole thing I'm going to talk about is basically about this. Solar wind charge exchange. Well, this is really simple. I don't need to go too much into details. You have a highly stripped ion from the solar wind. You have a neutral from the local interstellar medium. They get close together. If they get close, a tunneling of an electron from a neutral onto an ion is possible. The tunneling is resonant because, it can it can be any type of, but resonant has the largest cross section. So of course it occurs the most frequently. And therefore the electron finds itself. So energies are the same. The ground state and the neutral corresponds to some energy level in the newly formed ion. The ion is in the excited state. The electron in this ion is in the excited state. And then transitions occur once the electron goes from the excited state to the ground state. Right, we do have lots of minor ions. They're about 0.1% in general. It's not many of them, but we do have them. Their composition is dictated by how they are processed in the corona. It's collisional ionization. You can assume in the corona collisional ionization equilibrium, but once we go away, once the solar wind goes away, it gets diluted, collisions cease, and the solar wind coronal composition of the minor ions remains constant after that. And here we have observations. We have lots of observations on the minor ions. We know that pretty well. We know how, for example, fast solar wind and solar wind change, how they differ in terms of the ion composition and so on. Whether we can observe it, yes, of course we can observe. The first observation was by Rosat, and was observation of a comet, by the way. And of course, I think you know that, but for younger people, I should actually say just at least one word for that. It was really a surprise at that time, as far as I can tell, that an object which is really cold, just tens of degrees maybe, is producing X-rays, something that requires high temperatures. So that was kind of a mystery, but not for long. One can quickly understand that solar wind charge exchange occurs there really frequently because the comets are actually sources of neutrals, huge sources of neutrals, and therefore production rates of the X-rays are really strong in there. And one can check that this is actually true by looking at the spectrum, by the lines. And what I shown here is not actually the lines that observed. Of course, lines were observed, and that was confirmed. But what I show here is actually the lines that are obtained from laboratory measurements. So laboratory allows us to do charge exchange spectra, for example, for the solar wind type composition. So this is really great. One can observe coronal mass ejections, especially with interactions due to the interaction with this with the Earth. We have Chandra observations. We have many Chandra observations in the Chandra deep field north, or in the helium, I mean, in the direction of the helium core and sideways. And one can see actually, I just learned this actually from Jonathan, and I'm particularly grateful to him for pointing this emission to me, that I didn't bring this up, but I tried to find that graph, and indeed we do see that there is some difference between the directions where we're looking along the helium cone or sideways. So it means that indeed in the helium cone we do have charge exchange more frequent. Modeling is simple. Actually, what I'm going to do here is just briefly outline. I don't think I need to go too far. We're not doing full simulations with charge exchange, not yet. So we're doing charge exchanges post-processing. So we need the heliospheric model to reconstruct how gas moves. So here as an example, this is the density density plot. We use MS Flux, developed by Porgarello for a couple of decades, or 3 decades maybe now. Then we solve the evolution equations, basically continuity equations for each ion species. So we take all of the X-ray producing ions in the range of 200 keV or 100 keV down to 100 eV down to 1 keV. And we look for the evolution of all of them along the path of the gas, which we know now. And this, of course, is very simple. We have sync because we have charge exchange of these ions with neutrals, and they become ions with one less ionization state, Q minus 1. So that's the sink, and we have the source. Higher charged ions get an electron and become this ion. So that's the source. So we have sink and source. We have 45 species. Helium is not X-ray producing, but has a line at 70 eV. So and it's broad. So actually, it can add some emission. At around 100 eV. We have carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, iron, all of that you can see here. And the relative compositions, that's the reaction rates, but relative composition is actually the same. Then we need to calculate volumetric X-ray production rates, and surprise, surprise, that's of course just the source in the continuity equation, because a highly charged ion becomes of Q plus 1 charge becomes an ion with charge Q in the excited state. And then we have this cascade of X-ray, and not only X-rays, but all of the production of all of the photons. So essentially, X-ray production rate is the production rate for the ions. And here's how oxygen looks. That's 7 plus ions. This is oxygen 6 plus ions. That's how they look. By the way, you see that there are some differences between here and here. What's the difference? The difference is associated with the evolution. Evolution is associated with so-called collisional thickness. So an ion can experience certain collision within a certain time, and the gas input during this time also moves with certain velocity. So different distances from the sun, which is over here, you will see different, or you expect different number of collisions happening, charge exchange collisions. So up to here, you expect roughly 1 collision, down to here, 2 collisions, 3 collisions, 4 collisions. So an ion with charge Q becomes Q minus 1, Q minus 2, Q minus 3, and Q minus 4 at those boundaries. Of course, that's the ensemble average. I'm not saying that it's exactly 1, but that explains you. It's essentially like the optical depth, but the collision depth for the charge exchange. And in particular, I want to illustrate this collisional thickness effect on the evolution of neon. So neon 9 plus is like that. Most of it is near the sun, and a little bit goes into the tail. Then 8 plus is already bigger in the tail. Then 7 plus, then 6 plus, and 6 plus is already depleted near the sun. It has ionization potential lower than the temperature in the corona. So you have actually production of neon 6 ions far away from the sun. Neon 5 is absent at the sun, so all of it is produced by charge exchange. So true for the neon 4. So that's the collisional thickness effect. You can use it because all those pieces produce different lines. So if you observe a certain line or certain, I should say, a certain species, a certain atom with different ionization, not atom, but new should be atom, right? Ion, or say a neon or oxygen, at different ionization states, you have different lines. So by ratio of those lines, you can actually tell the morphology at different distances. So essentially, one can do tomography. Of course, question is what you can do with available X-ray instruments, but that's another story. We can still do good things there, especially as I told you about the temporal behavior. Then we can actually produce spectra. Spectra is produced if you know cascade probabilities and spectral line positions. That's a typical spectrum. I'm sure you actually know that. That's done for the XMM resolution, but in principle, the better the resolution, spectral resolution, the brighter the line looks, the brighter it shines on top of whatever background, galactic background you have. These are the dominant lines, the morphology of lines. And finally, one can get integrate those data along the line of sight from our location, which is nearly the solar location, outward, and get an information, get an all sky map of how all sky, I mean, the entire sky shines in a particular line. Here is an example of oxygen 7 line, the brightest one. And one can actually see that the nose and tail have differences, in particular, the brightness is like 50%. There are data, we have Chandra data, we have Rosat data in the past, still good one. We have Era Zeta, more recent one. One can use it as well. A few words about other stellar systems. The other stellar systems are no different from ours, except for different amount of wind that's produced. So the strength of the wind plays a role, and of course the environment where the star is located plays a role because you need to have neutrals. How observable those objects are. Well, with Chandra, probably not as good, but one can do something. With Rosetta data can already have something over there to analyze. Athena, the future mission, European mission, well, that's going to be fantastic if it's going to be there. It's a shame that we don't have here in this country anything like that. And just recently, a result was published that 3 astrospheres were observed in X-rays. So one can clearly see the excess emission. So blue line here in the spectrum, the blue line represents the solar spectrum. I mean, the stellar spectrum for each star, and the red one is the total spectrum. And the difference, of course, is what's produced by the star sphere, not the heliosphere, but the star sphere now. 7 were observed. 7 objects were observed, but only 3 actually were positive detections. So that tells us that one can actually do that. We already have those capabilities, and I'm sure Chandra can do as good as XMM. There's no doubt. So one should try, and on our side as theorists, we should actually develop the models, but we have to get also support from the observers here, because it's very hard to push such proposals through, because some people just say on the panels that these things are unobservable. Well, they are observable. And this is it. There's the conclusions. You can read them by yourselves. Thank you very much. Yes, right. Yeah, yeah.
There's the lab mission where some theory which might be interesting to this.
I haven't. I've heard about sounding rockets, which actually do nice observations because they have really great spectral resolution, and those lines actually shine brightly over there, way above the background. That's right. Yeah, yeah. So that's another possibility, definitely, and I hope that we will get from there as well. Okay, something very useful.
Just wondering if any of this can be seen from radio.
Radio dispersion.
Yeah, I mean, how the radio telescope direction change due to.
Probably one can, but that's a really delicate observation, right? Because the density contrast is not that big. I mean, you see here things not because the density is high, but because interstellar medium doesn't have the minor ions to produce charge exchange, and the solar wind does, right? And that's why it's shining bright. But the density contrast isn't that big. I mean, yes, there is some. A factor of 3, right? Because the ionization fraction is about 30% in the LISN. So yeah, maybe something. Yeah, good question actually. I have to look into that. Maybe there is something there, but it should be a delicate observation, definitely.
You mentioned chapter of it because the
Yes, there is a problem here. That's right. No, negative resolution is not important here at all. Yeah, spectral resolution is more important because if you make a spectrum, spectral lines thinner, then same amount is getting in the, it's squeezed, so they're brighter. And synchrotron background, for example, becomes subdominant. So yes, I would go that way. But probably there are trade-offs there. I'm not an observer, but it's very hard for me to make strong statements. Probably not as much, right? Because what we're talking about here is, again, are we talking about astrospheres or heliosphere? The heliosphere, well, it's the thing which is 4 pi around us, right? So it doesn't really matter. Well, the scales here, the scales that are involved here, as you have seen, Kelvin Helmholtz, for example, scale, 10 on the sky, right? So that tells you that it's not even a degree. In the direction, well, yeah, well, let's take a look. Yes, even in the direction of the tail, we're over here, right? So we're looking from here down through that. That's probably a few degrees, right? Where? Over here? That's where Chandra is. That's where the deep field, right?
Let's take our speaker again.
Thank you.